So let's take a look at some examples of primary active transport mechanisms. But before we do, just one more quick bit of review about this ATP molecule. If you haven't already, please see the previous video on ATP and how it works. Just want to add one more thing to that. You already know from that discussion that these bonds, right here and right here, are worth a tremendous amount of energy. And we talked about why. But I have one last question for you. Do you suspect that those two bonds are easy to break or difficult to break, and why? So here's a bond holding this phosphate group to this phosphate group. Do you think that bond is easy to break or difficult to break, and why? Pause the video, think about that, and then unpause it and we'll discuss. So what'd you come up with? What's your hypothesis? Easy to break, difficult to break, or why? Well, you can look at it from a couple perspectives. First, from a purely chemical perspective. Remember that this phosphate group has negative charges, so does this one. They don't want to be next to each other. That's why it was so difficult to get these two things to bond to the first place. Do you think it's going to be easy to disrupt the bond that holds them together, or difficult? It's going to be really easy because they still hate each other. Even though they're bound to each other, they still don't like each other. If you give them any kind of excuse, they're going to go running apart from each other. So that bond is actually really easy to break. A chemist might say that bond is very labile. Labile doesn't mean there's a lot of energy there necessarily. It means it's easy to break. So it's because, again, there's still, even though they're bound to each other, there's still repulsive force between this negative thing and that negative thing. And it would be really easy to just allow these two things to fly apart. It would be really easy to get this reaction to happen, the one that we already talked about. So that's one way to look at this. Another perspective on this is the following. If you're the cell and you want to do a lot of work all at once, you need a lot of energy. If I broke that bond, I'd have a lot of energy. Do you want it to be easy to break that bond or difficult? If I need to do some work now, I want access to that energy as easily as possible. If I want to go buy a $600 television at Best Buy, I would much rather have $600 bills in my pocket and I could just go and buy the television. That would be way easier than if I had, say, I don't know, some painting that was worth $600 that I had to then go sell at an auction and get some credit and then get that transferred into cash and then bring the cash to Best Buy. It's too many steps. It's too difficult. I want easy access to my money. The cell wants easy access to its energy. It wants that bond to be easy to break. And in fact, it is, for all the reasons that we just described about the repulsion between the two phosphates. So that bond and that bond happen to be very labile. With that in mind, let's take a look at an example of active transport. We call it primary active transport. We're going to look at others, but let's focus on this one for the moment. Again, inside of a cell, outside of a cell. I left some space here because we're going to need to draw a protein. And let's say that in this particular example, this cell really likes this particular substance. Maybe it's an ion, maybe it's a molecule. I'll just draw this little triangle to represent some substance that cell is really intent on hoarding. It really finds this stuff valuable. And let's say there's a low concentration of this stuff out in the environment. So the higher concentration of this material is actually inside the cell, but the cell still wants more. It wants to hoard this stuff. There are examples of this. I will give you questions that give you real-life examples of this. I want to use fake molecules right now just to illustrate the concept. So let's say that this cell says, gee, I have a lot of this, and I still want more. I want that one and that one as well. How am I going to get them? Diffusion's not going to help, because even if this stuff could get through the membrane, it's not going to go from a lower to a higher concentration. That's not going to help. Facilitated diffusion's not going to help. You can't use a passive mechanism to go from a lower to a higher concentration. So what are you going to do? Well, you build a protein. You put the protein in the membrane. Protein might look something like this. Here's a protein. That protein has two slots in it. One slot, that one, looks like it fits this object that you want. In other words, that fits right there. The shape matches, etc. So let's say this can land there. Well, that's fine, but you didn't really accomplish anything yet, right? All you did was bond this molecule that you desire to the protein. So what? Well, what if I could pay the entire protein to move? If I could pay it to, say, flip around in the membrane, to turn around 180 degrees in the membrane, well, then I would have gotten this object to the other side of the membrane because the whole protein that it's bound to flipped around in the membrane. How do I get a protein to change its shape so drastically? That's going to cost some energy. Well, I've got ATP. So take one of the many ATP that you have, you're the cell, take one of your many ATP and insert it into this little slot that's been pre-designed to accept an ATP molecule. As it lands in that slot, the protein will grab the ATP molecule and it will remove one of the phosphates. It will do that. In other words, it will ensure that this reaction happens. So the protein grabs onto the ATP, it hacks off one of the phosphate groups, and it spits out the parts, which is an ADP and a phosphate group. In other words, it does that reaction right there. But when that happens, a tremendous amount of energy gets released because you broke that bond and it's worth a lot of energy. That energy goes towards convincing this protein to swivel around or flip around, however you want to think of it, in the membrane so that this is here and this is here. Well, the object that you're trying to import is now on the other side of the membrane. You just imported that object. You went from a lower to a higher concentration. You had to pay for it. You had to pay for shipping. It cost you something, but you got the job done. You moved something from a lower to a higher concentration. So primary active transport is just this. You're moving one object for the cost of one ATP across a cell membrane, and since you're paying, you can decide to go from the lower to the higher concentration. You couldn't do that if you weren't paying for this. If this were a passive mechanism, this wouldn't work. But because you, the cell, is actually spending your own energy in the form of ATP, you get to decide you can go move this stuff from a lower to a higher concentration. You can hoard all this stuff that you want as long as you pay for every one that moves across your membrane. That's an example of primary active transport. I intentionally didn't put real chemicals in here because I'm going to eventually give you a follow-up question about this with some real-life application. So I just drew little triangles here as the thing you're moving, but that's essentially how this works.